Okay, so can you hear me? And like that? Yes? Okay. So I have bad news for you. So I am between you and the meal. So on the good front, so I am hungry too. So I will try to be quick. So I'm going to talk a bit about fuzzing and random testing. I don't know if you know what fuzzing is. No? Okay, so for those that know what fuzzing is, this will be very basic. For those, maybe you learn something, or I don't know, maybe you get something interesting for you. So, about me, for those that don't know me, so I am working in INRIA in the EBREF team with Stefan, Steven, Pablo, and other guys. I work on reflection now since some time in compilers, compiler testing, automatic testing, and so on. So, probably you know this quote from Distra. So everything that we test actually, so testing just shows us that there is some bug somewhere, yeah. But it doesn't tell us that there's an absence of bugs. Actually, probably Distra was thinking about doing formal verification on programs. But actually, what happens here, there's another lecture. Every time that we're writing a test, we are actually writing a regression test. And that test that we're writing is going to stay there, and it's going to detect a bug if we introduce it again in the system. Yeah, if we break something that we are testing. But the thing is that every time that we are testing, we have to think about the test cases that we're going to write, and maybe we miss some tests. Yeah. But at the end, what is powerful about a test suite is that it has to catch bugs. Yeah. So if we introduce a bug in the system, we need to be able to detect that bug again. Yeah? So a good test is a test that catches a bug when it comes back, because it's a regression test, the one that we're writing. But if we are actually only catching bugs that we thought about, this wouldn't be so interesting. So the question is, how can we actually look for bugs and write somehow tests that catch bugs that we didn't think about? Yeah? So in this direction, there was a guy, Barton Miller, in the 80s, that was working in his Unix station imagine 80s, so the internet was not what is right now. And he experienced some random crashes in some application he was running because of network connection, network errors. And he was thinking, okay, why isn't this more robust? Yes? So the guy thinking about this, he said, okay, I will make an assignment to my students. So he was an operating system teacher. And he said, okay, try to test some Unix utilities with some random inputs and see what happens. So 2 years later, he wrote a paper where actually he built a tool to automatically test Unix utilities. And he found that at that moment, 1/3 of the utilities he tested crashed with some random inputs. Yeah? So actually, he found a lot of bugs just giving random inputs generated by some tool. Yeah? So starting with this idea, something that we can do is, okay, we can build a random fuzzer that just generates random strings. Yeah, okay, and what can we do with this? Yeah, so I collect a collection, calling our random fuzzer, and then every time it will generate string with some random characters. Yeah, so these are 10 different strings. You know how to do this, just run a collection with a random size and then put a random character on that. And okay, so this is easy to do, and what can we do with this? So let's test the parser. Yeah, so I started playing with the asDate method. Yes, in Pharo, strings understand as date, and then they are supposed to give you a date for a string. And then you say, okay, I will take my random fuzzer, I will run it with a runner that does some stuff, and you will say, okay, for each input that I will fuzz, I will parse it with asDate and see what happens. Yeah? So this is in Pharo 11, as it is right now. And actually what you see here, actually what happens here with this block runner is that it will capture the exceptions and say, okay, if there was an exception, I consider this as a failure. There was a test that found a bug. And if it works okay, then I understand that there's no bug. Because since actually we are generating random stuff, the outputs also can be random. So actually generating how do we assert that this is okay? So right now we are saying, okay, if we have an exception, there's a failure. If we have no exception, it's okay. And then we find that actually there are a lot of inputs that pass, and we have dates. That's okay. And then we have failures with date errors, for example. Or we have here, look, that don't understand. There is a subscript out of bounds, so an out of bounds error, and so on. So we have a couple of errors there. Some of them look like bugs. Some of them actually don't look like bugs. Because we could consider that date error is a normal error that the parser is validating. So that's okay. That we can consider not as an error, but as actually as a valid input. So we can, out of these 60% of failures that we had, we can refine that a bit. And, for example, to consider what we learned here and say, OK, date error actually is an expected exception. Yeah? So I expect that to be an OK outcome of the parser. And then if we do that, we are in 5% of error, so which is OK. So OK, we have found 5% of inputs that kind of break the parser. They are to what look like bugs to me, so that's OK. So what else can we do? Now, we can try with other kind of fuzzers. We can try to configure a bit our random fuzzer with different ranges of characters and different sizes and so on to generate different kind of inputs. So for example, here has more alphanumeric outputs. Here, this one generates a larger set of characters. Yeah, so we can try to break the parser in different ways. When I run this with a couple of hundred times, so the first one that we saw, it was the weird chars. I called it weird chars. And then we had the second one that it was the large char set that generates a large character set. And the third one, it was the alphanumeric. What I saw is that 49% here passed, while actually here in this second, in these other two fuzzers, actually I broke the parser all the time, which is OK. Then we can study actually if those tests are actually bugs or not. But OK, we broke the parser, yes. But the thing is that, yes, these random inputs, they fail too easily, yeah. And of course, we are generating random bullshit. I'm going to say it like that. And the parser, of course, it could be a bit better at sanitizing the input and avoid these things. OK, we could try to fix that. But what happens if we try to generate almost correct inputs? Yeah, so we are generating kind of anything. And OK, what happens if we direct the fuzzer towards something that looks like a date? Yeah, something that quacks like a date, something that is maybe a date or maybe it's not a date. Yeah. So we need somehow to do that, a way to generate syntactically and semantically valid inputs, something that looks like dates. Yeah? And I will put the emphasis on syntactically here. We need something that actually in the string looks really like a date. So we can write a date fuzzer. If we can do that, we can write a date fuzzer, and then, for example, let's imagine that our date fuzzer can generate this kind of thing. So it can generate a number for a day, then a month, then a year, and with separators in the middle. And separators can be slashes, can be dashes, can be commas, can be spaces, I don't know. Yeah, something, so a date, separator. So OK, we can generate this kind of inputs. And how can we do this? Well, one way to do this is to use, for example, grammars. So probably everybody here knows that we use grammars to parse languages. Well, there is another way to use grammars, which is to generate things. Because grammars are actually just a description of language. So if we can parse the language and say that the input is correct respecting a grammar, we can also take a grammar and say, OK, I want to generate inputs that satisfy the rules of my grammar. So we can do that. Of course, this idea is from the 60s. It's nothing new, but it's not so much taught. So, but then we can write a grammar like this. Actually, this grammar was written by Adrien, that is there. No, this grammar I wrote. So he wrote the grammar library. I wrote this little grammar, so which is a grammar for a date. So let's look at it a bit. So we have numbers. Numbers are digits followed by a number or a digit. A digit is something that is goes from 0 to 9. Okay. And then what is a date? A date is a day, followed by a separator, followed by a month, followed by a separator, followed by a year, and so on. and we can follow the rules. Yeah. So this is a little DSL to write grammars, and then we can actually use this to generate stuff. We can generate strings from this. Yeah. So we can rewrite our date fuzzer as a grammar fuzzer using our grammar, and then actually now we can actually write any grammar and try to write any kind of input. And this will do the same thing that we wanted before. Now, if we try to use this grammar fuzzer with our parser, actually we find different kind of results. We find that here, in this case, 81% of the inputs passed, so they didn't generate any failure. We have expected failures, so here I'm separating them. So here, these are the date error exceptions. And we have 9% of failures. Yeah? So this has a high success ratio, of course, because we are now generating things like that look like dates. So I am expecting that the dates that I am generating will be parsed. So if we take a look at the bugs that we find, so again, so here I did it, for example, for 1,000 cases. We have the same method not understood that we found before. We have the same out of bounds that we found before, and we have some other validations with generic errors, so that some other new error appear there that we didn't have before. Okay. Now, it's okay. Now we can fast stuff. We can generate inputs. That's interesting to discover bugs that we didn't think about. But let's backtrack a bit. So before we were here, and we were just randomly generated inputs, and we were classifying the outputs somehow. But how did we classify those outputs? It was kind of arbitrary. I set the rule. Okay, this is a pass and this is a failure. How can we be a bit less arbitrary? Yeah, because the problem is that, again, if we're generating random inputs, we're going to get random outputs. And if we want to validate that, how do we validate the randomness? Yeah. So we need something that. Again, we have before decided that date error is an expected error, and we decided that that other kind of errors will fail when there is no failure. So when we get a date, actually we decide that it was not going to be a failure. But then actually something that happened that we didn't actually go deep into that is that we had these kind of inputs that actually were not failing. Yeah, I didn't actually make an emphasis on that. But all the things that were not failing were for this kind of input. So actually this thing gives a date. And this thing also, if you do as date for this thing, gives you a date. So then actually what is the date that is giving you? I don't know. Yes?
I was going to ask in your first slide, how was possible that those random 20 examples would give a valid date?
Well, the thing is that, yes, the parser is a bit lax. Yeah, he is relaxed. He says, yes, this is a date. That's OK. So we can consider that as a bug or not. It depends on the specification. But actually what happens is that this parser that is there inside as date, it's only expecting valid inputs. If you give random inputs, random things happen. Yeah. So it will never tell you that you are doing the wrong thing. So we should do something with that. But OK, we have this, and we have some rules, and we need to somehow say, OK, how do we validate this, and how can we also assert this? And actually, this problem of deciding if a random output from a random input is correct or not is something that is named the Oracle problem. Yeah, I'm not going to go in details in this, but this is research. So here, there's a whole area of research here, but it's given a program and given an input, how can we distinguish if that program had the right behavior or not? Yeah, so there's no straightforward solution for that, but we can do something. Yeah, there are some solutions. And that's actually the key here is not to decide if an input is, if a program regarding an input had the correct behavior. Is if we can do it automatically. Yeah, because if I can go manually and inspect each of the 100 things that I got, but if I fuzz 1 million inputs, then I cannot do it manually. So how can we do that? So what we need is assertions, right? So this is the thing that we are missing. With fuzzing, we were actually doing this part. We were generating this context and stimuli from the test, right? So we are generating the data that we're going to use against the program. But we are missing this check. And usually the checks that we're going to do, that we do, is assert that the result that we expect is equal to some value. The point is that this value, we don't know it, right? And we want to get that value. So how can we know what is the value that we need to put there to assert? So one idea is, for example, to use another parser. If we have two parsers for dates, we can actually compare both of them, and we can check if they agree or not in the outputs. Yes? So if they disagree, that means that there is a problem somewhere. If they agree, it means that, well, they agree. I cannot say much. Maybe there's a bug, the same bug in both of them. That is the worst case scenario. But the point is that we are looking for disagreements here. Yes? So, and with these disagreements will lead us probably to bugs. So fortunately, in Pharo, there's another parser. In Pharo 11 too, so it's a different parser, it's a different date parser. It's a parser that is structured, and it will actually follow a pattern, right? So we have this date parser that you can give it a stream, and then a pattern to read, and then it will actually build a date, reading this string from using this pattern that you are going to tell. Because actually, I don't know if you noticed before, but here actually we are making explicit the decision that a month is the first component of the date, and then the second one is the date, is the day. But the parser could actually have decided the other way around. We could have ambiguities. The as date actually is kind of ambiguous, because actually it will try to parse it like this, and if you pass something that a month that is not a valid month, it will actually try to parse it the other way around. So it's trying to be too smart there. Yeah. So now we have two parsers. What kind of comparison we can do between both of our parsers, and that are kind of fair, legal, safe. Yeah. And one thing is that, okay, I decided not to compare all possible patterns in a date. I decided to just compare this pattern, just for the presentation. Why? Because the asDate parser, the asDate, is going to parse like this. So if I want to compare the asDate parser with this parser, it's better if they are under the same conditions and they follow the same pattern, just to have some fairness there. So what we can do is we can change a bit our grammar, just to make a smaller grammar that just gives us dates in this format. Yeah, so we can just use a date that gives us month, separator, day, separator, year. And we don't have any other of the other patterns. Yeah. So we also say here that a month is a valid month, so it's either a digit or 11 or 12. Yeah, so we will have kind of valid dates here. And now that we have two parsers and a grammar to generate inputs from here, we can actually do differential testing. So differential testing is actually a way to test two systems by comparing their outputs if those systems have the same specification. So here we have two parsers that should follow the same patterns, so they should follow the same specification, and we can compare both outputs. So here I have two runners here. So we have a runner that will use asDate, a runner that will use the other parser, yeah? And then we have a differential runner that will run our Phuzzer or our grammar Phuzzer on both of them and compare the results, yeah? And then we can say, okay, what happens here? Well, can I find other kind of bugs? Because now we can do a better differentiation of the results. Now, I did this, and of course, what happens is that I had 100 times and only 3 errors. That is not a very cool result. So this thing here is not representative of that. It's just a copy paste. But so I only found 3 errors. Whoop. And that is actually because the data that we are generating are mostly correct. So I expect most parsers to be able to parse that, give me the same date, and then of course if we have the same date, I will have the same result. So there will be no bug in there. So actually we wanted to generate syntactically valid inputs, but slightly wrong. to try to go to corner cases. Yeah, so that is the thing that we actually want to do. And actually to do that, we have some ideas that I don't know if somebody, so probably most of you know something about mutation testing, which is add small mutations, small changes in the code to find bugs, let's say. Well, we can use this same idea to fuzz new input values. So we have input values that are almost correct, and we can actually mutate them to generate input values that are very, the ones that we were generating were correct, and we are going to generate values that are almost correct. So it goes kind of like this. So we have an input. We will apply a mutation, anything. You can think about any kind of change that we're going to do to the input. We are going to have a mutated input, and then we are going to execute the program and check if the result is OK or not using the same differential runner that we already have. So of course, this can be done using a mutation Phuzzer that we are going to have some seeds to mutate, so a corpus of data to modify. And it's going to run like this. So I'm going to take this Phuzzer, and I'm going to fuzz it 10 times, and then it's going to take this seed and mutate it, like adding characters, removing characters, switching characters, and so on. What kind of mutations we can think? Simple ones: insert a character, delete a character, swap a character by another one. So actually, with these simple mutations, we can already have probably very good results. So let's test with that. And actually, the thing that we are going to do is to chain the Phuzzers that we already have. So if we use for our mutation Phuzzer the inputs generated by our grammars, then we can actually generate from the grammar structure values, and then by mutating them, we can have probably structure values. They are probably correct. Yeah? And they are probably incorrect, too. And then I ran this 10,000 times to find stuff. And I had some interesting stuff. So actually, we had 68% of disagreement between both of them. Then we have to actually go and take a look at them. I grouped them by the signaler. It's written, no, it's not written anywhere. Yes, by the signaler context method and the program counter. So like that, I know that they are actually exceptions rise in the same place. So, and we have actually kind of seven different categories. Actually, what is funny is that we have some of them that have less than 1% of chance to be hit. So, of course, still with data, this is the error that we saw before, the same error we saw before. The input doesn't, so these errors we already saw before. These two are kind of new ones. Actually, I want to finish, to make a point in this one. So actually, we have, out of the 68 disagreements, a place where the asDate didn't find an error, but the other one did find an error. So I wanted to take a look at that one. So only 50 cases, which is less than zero, so it's 0.7% of the cases. Yeah. So actually, what happened here is it was that asDate was OK, and it was the other parser that was wrong. So actually, this was an interesting case because we were expecting that the other parser were correct to compare against our other parser. And here, actually, what happens is that the asDate was giving us the right result. So, and this case is actually, so you can actually play with this. There are many ways to reproduce this particular pattern, so this particular bug. The thing is that date parser, I checked it a little bit. So date parser accepts and ignores non-numeric characters in the year. So, and then it generates strange stuff. It's OK. It doesn't matter what it generates because it's buggy. So, but you can try this in your machines. So I want to finish with this and with some takeaways. So I would like that if you have to take something for you from this presentation, is that simple random inputs can unveil bugs. Yes, and that is the idea of fuzzing, is not to be able to generate a corpus of tests that we're going to run every time. Is that we're going to do a campaign to find bugs, to see if we have some that we didn't find before. Yeah. Now this random inputs can get random outputs, so we need some way to classify the outputs and see if they mean that we have a bug or not. So we can add some domain knowledge to make fuzzing more efficient, like for example, guiding the inputs with grammars or other techniques. We can have mutations. Actually, the mutations that I found, that I showed you, there were really simple mutations on strings. We can actually have mutations that are more domain specific, like swapping the day and the month, for example. We have seen that actually, if we have two programs that follow the same specification, we can actually use one to test the other one. Yeah. So that is the main takeaways of this talk. So thanks also to Adrien, that was the main leader of the implementation of the grammars, the generative grammars that are here in Yoko. So thank you very much. And we have 5 minutes for question and then go to lunch. Yes.
One error was stream has still more data.
Yes.
How do you detect that if the method is from string? Well, there is no stream where, but you have some specific detection if there's still more data.
So the question is, there was one error that is the stream has still more data. How good I detect that if I am using string? Actually, when you use a string as date, internally it creates a stream, a read stream on the string, and then it tries to parse it. The thing is that if you make a string that is a bit bigger than the date, so it has the date and then it continues, the two parsers they don't agree. So one of them will actually fail in one way, and the other one I think it will fail in another way. But I am not detecting it. Actually, it is the parser that is telling me that. So I am just running it and letting it fail. No? Okay, we can talk it later. Yes, Pavel.
Have you tried to mutate the grammar?
Adrien was working on mutating grammars, not by so far not by adding or deleting rules and so on, but actually I didn't show it, but the grammars actually support other features like hooks to do before and after each rule, and waits, because maybe you want a rule to be executed more often than other ones. And then what we played with, it was with mutating the weights to be able to actually guide the generation toward different paths. Yes?
Very cool work, and I like very much the fact that you can create easily your own Phuzzer and combine them. Have you just focused on strings and literals and numbers? Like, have you tried fuzzing on message stamps? Because this is, I think, where the state of the art ends. Fuzzing strings and numbers. There's been already quite some work on that, but then going to the next step, taking object translation to accounts.
Well, yes, so the question is, so I showed you only things that fuzz strings. Yes, of course, that's because so the presentation is easier to show like that. And Alex says, well, that actually the state of the art kind of ends there. How can we take object orientation into account? Actually, what Adrian's internship was about is how can we generate object graphs with these techniques. And one of the things that we were exploring was, okay, if I can generate strings, let's take this silly idea. I can generate strings that follow a grammar. I can generate JSON. And if I can generate JSON and then I deserialize it, I can generate an object graph. Yes? So, and the thing is, now, how can we tweak that to add types into account, for example, and generate an object graph to test applications? Yes, that are well, so we need to generate not only graphs, but also graphs that are well typed. So we were exploring a bit that. It's still ongoing. Yes?
So how do you integrate this with the continuous delivery or cost?
My short answer right now is that you don't. So the things that we can do right now are actually really fast to run. So yes, you can actually run a campaign, so run a million fuzzings every night, yes, if you want. And then you can store the inputs that fail. You can do that. Actually, what happens is that people run this in a controlled manner. Like they set a campaign. They say, okay, now we will run for 2 days a campaign of fuzzing, And then what you can do is you can take the things that are failing and create regression tests for that. You can automate that if you want also. But yes. Yes.
So how does the work on maybe the graphs and so on relate to things like property-based testing? So like things like quick check or stuff like that? Because that is fuzzing, but you constrain it and then make it.
So yes, you can think that types are kind of a grammar for objects. So if you have the type description of a class and all the graph of types and derivations, so you can think that you can generate a graph of objects following types. Yes.
Right. So that's quite similar then.
But yes. So that actually yes.
Yeah.
But so what happens in property-based testing is that yes, actually in quick check, you have a description of the types of your program. Usually, if it is in Haskell, you already have the types for free. So then you generate inputs, and then you specify properties, which are your assertions. So yes, they cover the oracle by handwritten assertions, for example. Yes.
You're familiar with AFL?
AFL, a bit, yes.
Okay. Did you think about going in that direction? Like reverse engineering fuzzing input from test coverage?
Yes. So one of the things is to integrate in here so a way to guide coverage using to guide generation with coverage. Yes. Right now, actually, the main objective of this is to have a little toolkit for us to use every day. First, second, to teach. I have to do that. So yeah. But yeah. So we were working a bit with coverage guiding the generation of inputs by coverage, but in other complex scenarios and not in this tool. So we were actually, this year, 23, but we did it last year. We were working on how to fuzz events for testing the garbage collector. And one of the things that we did there that was not published yet, but it was so if we can generate events for the garbage collector, like allocating objects and running the GC and so on, trying to crash it, how can we guide this generation to try to cover different passes in the garbage collector using code coverage? Yes, but okay, lunch.